In this question we are given that a die is rolled and E be the event that die shows 4 and F be the event that die shows an even number. Are E and F mutually exclusive? Let's begin with the solution. Now we know that when a die is rolled, the possible number of outcomes are 6. So the sample space, let us denote it by S, is a set having numbers 1, 2, 3, 4, 5 and 6, since these are the 6 possible outcomes when a die is rolled. We are given that E is an event that the die shows a number 4, therefore E is a set having only one element 4, and F is an event that the die shows an even number, and the even numbers from the sample space as we can see are 2, 4 and 6. So here we have 2, 4 and 6. We have to check whether E and F are mutually exclusive. First let us find out E intersection F. As we can see, E intersection F is a set having one element which is common to both the sets, and that is 4, which is not an empty set. This implies that E and F are not mutually exclusive, and this is because we know that two sets A and B are said to be mutually exclusive if A intersection B is equal to 5. That is, the occurrence of any one of them excludes the occurrence of the other event. That is, both the events cannot occur simultaneously. And here, as we can see, E and F are not two disjoint sets, therefore they are not mutually exclusive. This completes the solution. In this question we are given that a die is thrown and we have to describe the following events. Also we have to find A union B, A intersection B, B union C, E intersection F, D intersection E, A but not C, D but not E, E intersection not F and not F. So let's begin with the solution. And here the experiment is that a die is thrown and we know that the possible number of outcomes when a die is thrown are 6. Therefore, the sample space is a set having the numbers which appear on the face of the die, which are 1, 2, 3, 4, 5 and 6. Let us now define the events. The first one is a number less than 7. A number less than 7 which belongs to the set SR1, 2, 3, 4, 5 and a 6. So we see that A and S are equal sets. So this is equal to S. Now let us define the second event, which is a number greater than 7. Now from the sample space S we can see that there is no number in the sample space which is greater than 7. Therefore B is an empty set, or we can also say that B is an impossible event. Now let us move on to the third part. In the third part, C is an event such that they are a multiple of 3. Now from the sample space S we can see that there are only two numbers which are multiples of 3, which are 3 and 6. So there are two outcomes of the event C. Now let us find the fourth part. In the fourth part we have a number less than 4, and from the sample space we see that number less than 4 are 1, 2 and 3. So there are 3 outcomes to the event D. Moving on to the next part. An even number greater than 4, and from the sample space we can see that even number greater than 4 is 6. So this is a simple event having only one outcome. Now the sixth event is if such that a number not less than 3, therefore the numbers are greater than or equal to 3, and the numbers which are greater than or equal to 3 from the sample space S are 3, 4, 5 and 6. So hence we have described the 6 events. Now let us first find A union B. A union B will be a set having elements of A and B both. So A is the whole sample space S and B is an empty set. So we have 1, 2, 3, 4, 5 and 6 union the empty set, and this is equal to the whole set S. Next we have to find A intersection B. Again the set A is the whole set S. We have to find its intersection with the empty set, and this gives the empty set or an impossible event. Next let us find B union C. Now B is an empty set and we have to find its union with the set C, which has 2 outcomes 3 and 6. So this is equal to the set 3 and 6, or we can say that this is equal to the event C. Next we have to find E intersection F. Now E is a set having only one outcome, that is 6, and we have to find its intersection with the set F, and that has 4 outcomes 3, 4, 5 and 6. So this is equal to the set having only one element, which is 6, or we can also say this is equal to the event E. Next let us find out D intersection E. Now D is an event having outcomes 1, 2 and 3. We have to find its intersection with the event E, and the event E has one outcome, which is 6. So their intersection is an empty set. Next we have to find A but not C. Now the set A is a set having all the 6 outcomes when a die is thrown. From this we have to subtract the event C, and the event C is a set having 2 outcomes 3 and 6. Therefore this is equal to 1, 2, 4 and 5. Therefore A but not C is a set having 4 outcomes, which is 1, 2, 4 and 5. Now let us find D but not E. Now the set D has the outcomes 1, 2, and 3 since a number less than 4. So the number less than 4 from the sample space are 1, 2 and 3 minus the event E, which is having one outcome, that is 6. So this is equal to the same set D having the same 3 outcomes, 1, 2 and 3. Now let us find out E intersection not F. So E is a set having one outcome, that is 6, intersection not F. This is equal to 6 intersection. Now the sample space S has 6 outcomes and F has outcomes 3, 4, 5 and 6. Not F are the outcomes which are not in F. So outcomes are 1 and 2. So their intersection is again an empty set since they do not have any outcome in common. Therefore, E intersection not F is an impossible event or an empty set. Now we have to find not F, and this we know that this is S minus F, which we have already found. That is S but not F, and this is equal to the sample space but not the set F, and this therefore has outcome 1 and 2. Therefore, not F is a set having 2 outcomes, 1 and 2. This completes the solution. This question says an experiment involves rolling a pair of dice and recording the numbers that come up. Describe the following events. The first event A is the sum is greater than 8. The second event B is 2 occurs on either die. Third event is the sum is at least 7 and a multiple of 3. Then we have to find which pairs of these events are mutually exclusive. Let's begin with the solution. Now, we know that when a dice is rolled, then the possible outcomes are 6. So here, we are rolling 2 dice. Therefore, the possible number of outcomes are 6 raised to the power 2. Which is equal to 36. Let us denote the sample space by S. On rolling the first die, the possible outcomes are 1, 2, 3, 4, 5 and 6. Then the second die is rolled. Then after this there are 6 more possible outcomes, and the first pair is 1, 1, 1, 2, that is a 2 can appear after 1 on the second die. Then 1, 3, 1, 4, 1, 5 and 1, 6. Similarly, after the first die is rolled, if we get a 2, then again the dice is rolled, and then we get 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6 and so on. We continue with 3, 4, 5 and 6. Therefore, the sample space is the set of pairs x, y such that x and y belong to the set of numbers 1, 2, 3, 4, 5 and 6. So this is the sample space. Now let us write down the event A. A is the event that the sum is greater than 8. That is, sum of x and y is greater than 8 we have to find out. So, this implies that the sum should be equal to 9, 10, 11 and 12, since the maximum sum is of the pair 6, 6, which is equal to 12. Therefore, if the sum of x and y is greater than 8, the numbers can be 9, 10, 11 and 12. So, the set will have the outcomes 3, 6, 6, 3, 4, 5, 5, 4. Then we can have 6, 4, 4, 6. Then we can have 5, 5. Also we can have 5, 6, 6, 5. And the last one is 6, 6. So this is the set A. Right? Now let us write down the event B. The event B is that 2 occurs on either die. So if 2 occurs on the first die, then in the second die, the numbers from 1 to 6 can exist. Now we can have 2 on the second dice, and the first die will have the number from 1 to 6. So we have 1, 2. Now if we write 2, 2, then we see that it will get repeated by this 2, 2. Therefore, we proceed on to the next one. We get 3, 2. Then we get 4, 2. Then we get 5, 2. And finally 6, 2. So this is the event B. Now let us find the event C, which says the sum is at least 7 and a multiple of 3. This implies that the sum is either 9 or 12, since they are greater than 7 and 9 and 12 are multiples of 3. So now let us find out the sum of the pair, which is equal to 9 and 12. So this is the set having elements 3, 6, 6, 3, 4, 5, 5, 4 and 6, 6. Now we have to find which pairs of these events are mutually exclusive. Now as we can see, the set A is having all the pairs whose sum is greater than 8, and in set B, as we can see, the sum is maximum 8. Therefore, A and B are mutually exclusive. Since A intersection B is equal to 5, that is an empty set, this implies that A and B are mutually exclusive. Now let us check the sets A and C. Now in the set A we have a pair 3, 6, and in the set C we have a pair 3, 6. This implies that A intersection C is not equal to an empty set. Therefore, A and B are not mutually exclusive. Finally, let us check the sets B and C. As we have seen that sum is maximum 8 in case of the set B, and set C is the set of elements having the sum 9 or 12. Therefore again, B and C are mutually exclusive since they do not have any element in common. Therefore we can say that B and C are mutually exclusive. Right? Hence our answer is, we have to find out which events are mutually exclusive. Therefore event A and B, and the second pair is B and C, are mutually exclusive. This completes the solution. This question says that 3 coins are tossed once. Let A denote the event that 3 heads show, B denote the event that 2 heads and 1 tail show, C denote the event that 3 tails show, and D denote the event that a head show on the first coin. We have to find that which events are mutually exclusive, simple and compound. Let's begin with the solution. Now, we know that when a coin is tossed, the possible outcomes are 2, a head or a tail. So the possible outcomes are 2, and here 3 coins are tossed once. Therefore, the total possible outcomes is equal to 2 raised to the power 3, and this is equal to 8, since when 3 coins are tossed once or 1 coin is tossed thrice, the sample space is the same. Therefore, in this case, the sample space is HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. So this is the sample space for this experiment. Now let us define the event A. The event A is 3 heads show. So it will have only one outcome, having H, H and H. Now let us write down the event B. Event B is 2 heads and 1 tail show, and from this sample space, this comes under event B. Since here we have 2 heads and a tail, this also comes under event B. This also comes under event P. Now let us write down the event C. The event C is a set in which 3 tails show, and the 3 tails are shown only once in the sample space. Therefore, event C will also have only one outcome. Finally, let us write down the event D. It is a head shows on the first coin. Now from the sample space, let us write down the outcomes where the head is shown on the first coin. This comes under D. HHT also comes under D. HTH also belongs to the set D. And HTT also belongs to the set D. Now let us answer the question. First we have to answer which events are mutually exclusive. So, as we can see, the set A and B are disjoint sets. Also, sets A and C are disjoint sets since they have no element in common. Also, we have B intersection C is equal to 5. Therefore, these two sets also do not have any element in common. Also, D and C are disjoint sets since they also do not have any sample point common. Therefore, we can say that A and B, A and C, B and C and D and C are mutually exclusive events. Now let us proceed on to the second part. In the second part, we have to find which events are simple. Now we see that the event A and C have only one sample point of the sample space. Therefore, events A and C are simple. Hence, our answer is events A and C are simple events. Since they have only one sample point of the sample space, therefore they are simple events. Now let us proceed on to the third part, in which we have to answer which events are compound events. Now, as we can see, events B and D have more than one sample point of the sample space. Therefore, B and D are compound events. Hence, our answer is events B and D are compound events. This completes the solution. In this question, we are given that 3 coins are tossed. We have to describe 2 events which are mutually exclusive and 3 events which are mutually exclusive and exhaustive. So let's begin with the solution, and we know that when a coin is tossed, the total possible outcomes are 2, a tail and a head. Right? Therefore, here we have 3 coins. Thus we can say that the total possible outcomes for this experiment is 2 raised to the power 3, which is equal to 8. Thus the sample space has the 8 outcomes as HHH, HHT, HTH, THH, then HTT, THT, then we have TTH, and then TTT. Let's answer the first one. Here we have to define 2 events such that they are mutually exclusive. So let the events be E and F. Be the 2 events. Now let us consider E as the event such that one head and 2 tails show up, and F denote the event such that one tail and 2 heads show up. Thus we have E as the set having one head and 2 tails. So we have HTT, THT, and then TTH. And F is the set having one tail and 2 heads. So we have HHT, HTH, and THH. Now as we can see from here that E intersection F is an empty set. Therefore, E and F are mutually exclusive events. Now let us proceed on to the second part. In the second part, we have to write three events which are mutually exclusive and exhaustive. So let E, F and G be three events such that E intersection F is equal to F intersection G is equal to E intersection G is equal to an empty set, and their union, that is E union F union G, is equal to the whole sample space is. Let E be an event such that not more than one head shows up. So this implies E is a set having the outcomes tail, tail, tail. Maximum one head can be there. So we have head, tail, 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 head, tail, and then tail, tail, head. So there are four possible outcomes. Let us define now F. Let F be the event that exactly two heads show up. So we have F having the outcomes head, head, tail, head, tail, head, and then tail, head, head. Now let us define G. Let G be the event that exactly three heads show up. So G is an event having elements head, head, and head. Now from here we can see that E intersection F is phi, since they do not have any sample point in common. F intersection G is also a null set, and E and G is also an empty set. And also E union F union G gives the whole sample space S. Therefore, E, F and G are the required three events which are mutually exclusive and exhaustive. Hence our answer is E, F and G are mutually exclusive and exhaustive. This question says that three coins are tossed. We have to describe two events which are mutually exclusive, two events which are mutually exclusive but not exhaustive, and three events which are mutually exclusive but not exhaustive. Let's begin with the solution. And as we can see that this is the continuation of question number 5. So here the sample space is the same, having 8 outcomes, which is HHH, HHT, HTH, THH, HTT, THT, TTH and TTT. Let us now find the solution to the third part. Here we have to find two events which are not mutually exclusive. So let E and F be the two events such that E is an event which shows not more than one head. So E is a set having outcomes TTT, HTT, THT and TTH. Here notice that TTT also belongs to this set since it has no head. Now let us define the set F. F is no head shows up. So there is no head. So this event has the outcome tail, tail, tail. Now as we can see, the sets E and F is not equal to 5, that is E and F are not disjoint sets since T, T, T are common to both the sets. Therefore, E and F are not mutually exclusive. Let us now proceed on to the fourth part. Here we have to write two events which are mutually exclusive but not exhaustive. So let us define E and F such that event E is such that one head and two tails show up, and F is an event such that one tail and two heads show up. Then E will be a set having the outcomes head, tail, 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 head, tail, 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 head, and F will be a set having outcomes head, tail, head, 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 tail, and tail, head, head. Now from E and F we can see that these two sets are disjoint sets and their union is not equal to S. Therefore we can say that E and F being two disjoint sets are mutually exclusive but since their union is not equal to the whole sample space S, therefore they are not exhaustive. Now let us proceed on to the last part. In this part we have to write three events which are mutually exclusive but not exhaustive. So consider the events E such that only one head shows up, F such that exactly two heads show up, and G such that three heads show up, right? So E will be a set having elements HTT, THT and TTH. F will be the set having the sample points exactly two heads show up, that is head, head, tail, tail, head, head, and head, tail, head. And G is a set which has 3 heads. So we have head, head, head. Now from here we can see that E intersection F is an empty set, F intersection G is an empty set, and E intersection G is an empty set. Therefore, E, F and G are mutually exclusive events. But since E union F union G is not equal to S, since the outcome tail, tail, tail do not exist in any of the 3 events, therefore it is not equal to the whole sample space S. Therefore, the E, F and G being mutually exclusive are not exhaustive. So they are not exhaustive. This completes the last part. In this question we are given that 2 dice are thrown and the events A, B and C are as follows. We have to describe the following events. Let's begin with the solution. We know that when a dice is thrown, the possible number of outcomes are 6. Therefore, in this case, we have 2 dice which are thrown. Therefore, the total possible number of outcomes are 6 raised to the power 2, which is equal to 36. Now let us write down the sample space for this experiment. Sample space consists of all the ordered pair XY such that XY belong to the set of numbers 1, 2, 3, 4, 5 and 6, which are the 6 faces of a dice. Or this can further be written as, if X takes the value 1, then Y can take the values from 1 to 6. So we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6. Now if X takes the value 2, then Y can again take the value from 1 to 6. So this way, this is the required sample space for the given experiment when 2 dice are thrown. Now let us find the event A. The event A is getting an even number on the first die. Now we see that the second row, the fourth row and the sixth row in the sample space have the first element as 2, 4 and 6 respectively. Therefore, in these 3 rows, we have the first number as an even number. Therefore, A consists of the ordered pair of the second, fourth and sixth row. So the numbers are 2, 1, 2, 2 and so on. These are the required ordered pairs of the event A. Now let us find the event B. Event B is getting an odd number on the first die. Now again from the sample space, we see that the first row and in the third row and in the fifth row, for these 3 rows, the number in the first die is an odd number, 1, 3 and 5 respectively. Therefore, the ordered pair or the sample points in the first row, third row and fifth row belong to the event B. So first we have 1 1, then 1 2, 1 3, and so on. So this is the required event B. Now let us find C. C is getting the sum of numbers on the dice less than or equal to 5. That is, the number x plus y must be less than or equal to 5. Now from here we see that 1 1, 1 2, 1 3 and 1 4 is less than or equal to 5 in the first row. From here we get 2 1, 2 2 and 2 3. From the third row we get 3 1 and 3 2 and 4 1. So for these 10 numbers, the sum of x and y is less than or equal to 5. Therefore, the event C consists of the ordered pairs 1 1, 1 2, 1 3, 1 4, then 2 1, 2 2, 2 3, then we have 3 1, 3 2 and then 4 1. So these are the 10 sample points which belong to the event C. First let us describe the event A naught. So this is equal to not A, in other words, that is the whole sample space minus the event A. Now if we consider the event A, we see that the first number of the ordered pair is an even number, and if we subtract all these ordered pairs from the whole sample space, we get the first, third and fifth rows such that their first number is an odd number. That is, we get the event B. Therefore, S minus A is nothing but event B. Therefore, A naught is equal to B. And this is because A union B is the whole sample space and A intersection B is the null set. Now let us find the second one, which is not B, and not B is nothing but the whole sample space minus the event B, and this is equal to A, as A union B is equal to the whole sample space is and their intersection is a null set. Therefore, if from the whole sample space we subtract the event that getting an odd number on the first die, then we get an event of getting an even number on the first die, which is event A. Now let us proceed on to the third part. In the third part we have to find A or B, and A or B can also be written as A union B. And since A is an event of getting an even number on the first die and B is an event of getting an odd number on the first die, therefore their union gives the whole sample space S. Since from the sample space we know that second, fourth and sixth row show event A, and first, third and fifth row shows the event B. Therefore, A union B gives the whole sample space S. Now let us proceed on to the fourth part. In the fourth part we have to find A and B. A and B is nothing but all the omegas such that omega belongs to A and omega belongs to B. That is, we have to find A intersection B, and this is nothing but the null set. Since A and B do not have any sample point in common, therefore A and B is nothing but an impossible event. Now let us proceed on to the fifth part. In the fifth part we have A but not C. That is, we have to find all the ordered pairs which are in A but not in C. So all the sample points which belong to A but not in C are the sample points which belong to A such that their sum is greater than 5. So such pairs are 2, 4. This is a pair such that its first number is an even number and their sum is greater than 5. Then we have 2, 5. Then we have 2, 6. Then we have 4, 2. Then we have 4, 3. Then we have 4, 4. Then we have 4, 5. And 4, 6. And then we have 6, 1. 6, 2. 6, 3. 6, 4. 6, 5. 6, 6. And this is the required A but not C event. Now let us find the next one, which is B or C. B or C implies B union C. Now B is an event of getting an odd number on the first die and C is the event of getting the sum of numbers on the dice less than or equal to 5. So this is equal to, which is equal to all the omegas such that omega belongs to B or omega belongs to C. So this is an event which will have all the ordered pairs or the sample points of the event B and C. So these are all the sample points of the sample space S which belong to the event B, and now let us write all the sample points which belong to the event C, and they are 2, 1, 2, 2, 2, 3 and 4, 1. So this is the required event B or C. Now let us move on to the next one. It is B and C. That is B intersection C, or we can say that all omega such that omega belongs to B and omega also belongs to C. That is, all the sample points which belong to this event should have an odd number on the first die and the sum of the numbers on the dice should be less than or equal to 5. So such numbers are the ordered pairs 1, 1, 1, 2, 1, 3, 1, 4, then we have 3, 1 and 3, 2. Now let us move on to the last part, which is A intersection B naught intersection C naught. Now taking the first two, we have A intersection B naught intersection C naught, and from the second part we know that B naught is nothing but A. So we have A intersection C naught, and this is equal to A intersection C naught. So this will have all the sample points such that the first number is an even number and their sum is greater than 5. So the numbers are 2, 4, 2, 5, 2, 6, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5 and 6, 6. So these sample points belong to the event A but not C. So this is nothing but A intersection B naught intersection C naught. So this completes the solution. This question is the continuation of question number 6 of exercise 16.2, in which we were given that two dice are thrown and the events A, B and C are as follows. We have to state whether the following given 6 statements are true or false. Let's begin with the solution. And we are given that two dice are thrown, therefore the sample space for this experiment is the set of all ordered pairs x, y such that y belong to the set of numbers 1, 2, 3, 4, 5 and 6, which are the 6 faces of a die. Now let us write the sample space S by putting the values of x and y. So this is as follows. Now let us write down the event A, which is of getting an even number on the first die. Now from the sample space we see that the second row, fourth row and the sixth row of the sample space have even number on the first die. Therefore the sample points of the second row, fourth row and sixth row are the outcomes of event A, which are as shown. Now let us write the event B. Event B is getting an odd number on the first die, and from the sample space we can see that the first row, the third row and the fifth row has the odd number on the first die. Therefore the outcomes of first, third and fifth row are the outcomes of event B. Therefore event B is as follows. Now let's write the outcomes of event C, which is of getting the sum of numbers on the dice less than or equal to 5, and from the sample space we see that 1 1, 1 2, 1 3, 1 4 from the first row, 2 1, 2 2, 2 3 from the second row, 3 1 and 3 2 from the third row and 4 1 from the pairs such that the sum of the numbers is less than or equal to 5. Therefore these numbers belong to the set C, which are as follows. Thus we have got the events A, B and C. Now let us answer the given statements are true or false. First one is A and B are mutually exclusive. So this is a true statement since A and B are disjoint sets. Since A is an event of getting an even number on the first die and B is an event of getting an odd number on the first die, therefore the two events A and B are disjoint and hence A and B are mutually exclusive events. Now let us proceed on to the second part, which says A and B are mutually exclusive and exhaustive events. Now we see that A intersection B is an empty set since they are mutually exclusive. Also, if we find A union B, we see that A comprises of the second, fourth and sixth row of the sample space and B comprises of the first, third and the fifth row of the sample space. Therefore, A union B gives the whole sample space S. So we have A union B is equal to S. So from here we get that A and B are mutually exclusive, and since A union B is equal to the whole sample space S, this implies that A and B are exhaustive events. Hence, the second statement is true since A intersection B is equal to 5 and A union B gives the whole sample space S. Now let us find the solution to the third part. It says A is equal to not B, and not B is nothing but the sample space, but not B. And if from the sample space we delete the outcomes of event B, we get all the outcomes of event A of getting an even number on the first die, right? Hence, the third statement is also true, and this is since A is equal to S minus B, which is equal to not B. Now let us proceed on to the fourth part, which says that A and C are mutually exclusive. This is false, since A intersection C, let us check it out, if they have any ordered pairs in common. Now we see that A has an ordered pair 2, 1, and C also has the same ordered pair 2, 1. Similarly, we can find many sample points which are common to both A and C. Let us see for one more. 2, 2 is a sample point of the event A. Also 2, 2 is the sample point of event C. Therefore, we have one more point which is common to both the events A and C. So this way we can find some more. Hence A and C are not disjoint sets, and therefore they are not mutually exclusive. Now let us proceed on to the fourth part. Now we are proceeding on to the fifth part, which says A and B naught are mutually exclusive. This statement is false, and this is because if we find A intersection B naught, this is equal to A intersection B naught is nothing but A. This is because B naught is S minus B, and from the sample space, if we delete all the outcomes of event B, we get A. And A intersection is A, which is not an empty set. Therefore, A and B are not, A and not B are not disjoint sets. Therefore, they are not mutually exclusive. Hence, this one is also false. Proceeding on to the last part, which says that not A, not B and C are mutually exclusive and exhaustive events. Now, let us first find the intersection of not A and C. So this gives event B and C, and B and C, we see that there are sample points which are common to both B and C. Hence, these two are not disjoint sets. So not A can be written as B intersection C, and we see that this is not a disjoint set. Similarly, if we find not B intersection C, we see that this is also not an empty set. Therefore, not B, not A and C are not mutually exclusive. since from here it implies that not A and C are not mutually exclusive and not B and C are not mutually exclusive. Therefore, all the three are not mutually exclusive and hence they are not exhaustive. So, the answer to the last part is false. And the reason is, since not A intersection C is not equal to an empty set and not B intersection C is not equal to an empty set. So the answer to the sixth part is false and this completes the solution.